Hello and welcome to video number 22. My name is At-Taib Abul Yaman and this video is about a function. Basically, this is just the very basic elementary characteristics of functions that everybody need to know if they are to proceed with studying calculus. So let's start with a definition. If the value of a variable y depends on the value of another variable x, then y is said to be a function of x denoted by y equal to f of x. A function is distinguished from a relationship in that each value of the variable x in the function's domain is related to only one and only one value of the variable y in its range. As such, every function is a relationship, but not every relationship is a function. We're going to elaborate on this one later on, but for now, let's jump on the basic characteristics of a function. We can say that a function is a relationship between two variables. One is the independent variable, and normally that is the x, and the other one is the dependent variable, and usually that is y. A function has a domain for the independent variables' values and a range for the dependent variables' values. A function connects each value in its domain to a single value in its range. The connection could be one-to-one. It could also be many-to-one. Here is an example. Obviously, this example is one-to-one because we have three elements in the domain, three elements in the range, and every element in the domain is mapped to a unique element in the range. And that's why this is an example of a one-to-one mapping. One-to-one mapping. A function may be many-to-one. By many-to-one, we mean the function connects more than one value in the domain to a single value in the range. Let's take a look at example. Here we have two elements from the domain, namely 1 and 3, as connected to C. So both are mapped to C, and that's what we meant by many-to-one. And many-to-one connects more than one value in the domain to a single value in the range. Also, a function may connect all values in its domain to all or some values in its range. We call it all to any. So in this case, we have all connected to some, not to all. All connected to some because B is not mapped to. We have another example here, all connected to all, because every one of them is mapped to. And then we could have also all connected to only single one element. And this is a special function. It has a special characteristics, and this could be a linear function. This actually is a linear function. So a function that is linear, we will talk about it later on. It connects every value in its domain to the same value in its range. Every value of the domain, the 1 and the 2 and the 3, are connected or mapped to a single value C. So a function is a linear function if it connects every value in its domain to the same value in its range. Such function is even if its domain is the set of real numbers. And by even, we mean the function is symmetric around the y-axis. Here is the plotting of the function. Obviously, this function in the domain, it has just three elements, and that's why we have 1, 2, and 3. And if we read f of x, when x is equal to 1, f of 1 is equal to c, f of 2 is equal to c, and f of 3 is equal to c, which is similar to the diagram over here. So the same information in the diagram, we have it in the plot. This is the graph of the function. Now we will go ahead and discuss the diagrams in 2 and 3. Let's take a look at the diagrams. Obviously, this diagram represents something that is not a function. That's a relationship, not a function. The reason being, we said that the function maps every element in its domain. Since this particular diagram does not map every element in its domain, so it's not a function, because 2 is not mapped. So we can call this one relationship. So relationship is not a function. A function is a relationship, but relationship is not a function. Let's go ahead and take a look at example number 3. Example number 3, if we look closely, we can see that 2 is connected to more than one element in the range. So that's a violation also for the function, because each element in the domain must be mapped to a single element in the range. But in this case, we have this diagram maps 2, which is an element in the domain, to more than one element in the range, and for that reason it's not a function. So this is a relationship. This relationship will result in a jump, as we will see in a minute. If we want to plot this function, we know that the domain contains 1, 2, and 3. So 1, 2, and 3 are values of the independent variable x, and the values of y that correspond to x equal 1 is c, and to x equal 3 is c, the values of y. So we can see that when is equal to 1, the value is c. When is equal to 3, the value is c. But when x is equal to 2, the value of f of x is a or b. So the value of f of x here is either a or b. Now if we want to draw the function, we could probably go from 1, which has a y value equal to c. We go to visit 1 to visit a, and then we come back to c, and that way we will draw the curve. But one thing that we have to make sure is the fact that this function is not just f of 2 equal to a. F of 2 is also equal to b. That means we have to also draw a curve coming from c, visiting b, and then going back to c. So this is the curve. As we see here, we have a function that looks like a human face, probably not an oval, not a circle, but it has something in common between ovals and circles. If we draw the vertical line across the function, we will see that the vertical line intersects the function in 2 points, and this is called the vertical line test. So this is not a function. Why? Because the value of y is ambiguous, at least for the number 2, but it's ambiguous for more than 2. But for example here, we're just saying the value of 2 is ambiguous. F of 2 is ambiguous, and that's why it's not a function. Because you can say, okay, 2 is mapped to a or 2 is mapped to b. So that's ambiguity. Okay, that's it. Let's just go ahead and summarize. For diagram number 2, the answer is that it's not a function, it's a relationship, because the domain element 2 is not mapped. We've explained that. For example 3, we said it's not a function because it violates the vertical line test. The vertical line test proves that the vertical line meets the function at 2 points, which is not allowed. So it's not a function, it's a relationship. Let's take a look at the characteristics of functions from different perspectives. What we will do here is we will put in the domain and range, and then we have a note here. Unlike a function, a relationship allows a vertical line to connect two or more points on the function's graph. Below is a relationship that does not qualify to be a function since it fails the vertical line test. And we've gone through this example, so I'm not going to waste time on it. You can go back to the previous slide to check it. Now, we want to look at a diagram on the left here and see if it represents a function, and if it is not, then we have to justify our answer. Here is a diagram. Okay. Does this diagram represent a function? Justify your answer. If we look, we can immediately spot the number 2, which is a member of the domain. It's mapped to more than one element in the range. And this mapping will result in the vertical line test failure. So this is not a function. This is not a function. So that's the reason we put this particular test graph over here. Let's go ahead and take a look at real world functions. So this is the domain and this is range, and the data is from real world data. We want to check to see if the function is continuous and if the function has inverse. To start with, let's do some definitions. What makes a function continuous and what makes a function have an inverse? For continuous, definition number 1 says a function is continuous if it does not have jumps, and between any 2 points on its graph there are infinitely many points. Definition number 2, a function has an inverse if and only if it is a one-to-one and onto function. Last, domains contain a few sample points. We're not going to put all the points of the domain in the domain that we're going to demonstrate. If, for example, the domain is the set of all real numbers, we cannot write the set of all real numbers in this small screen or in any screen of any size for that matter. So we're just going to select elements from the domain, representatives of the domain, and put them in it. So let's go ahead with the first function. We want to look at the score of a student and the grade the student will earn. And this is a relationship between the score and the grade, and we want to see if it is a function, if it is continuous, if it's not continuous. So the sample that we have is the student grades are 71, the numerical grades, 92, and 75. You could just call them the percentages if you wish. So this is mapping of the final total to the grade the student deserves. We can see that 71 is mapped to a C, 75 is mapped to a C, and 92 is mapped to an A. So the grade is equal to the function of score. So f of 71 is C, f of 75 is C, f of 92 is A. And we can see that we did not map anything to the letter B in the range. So question, is this function continuous? It may not be obvious to determine whether the function is continuous or not just looking at the diagram. So let's provide a plot, a graph of the function. Here is the graph of the function. There are a few points that we have to pay attention to. We have the function defined between the point 70, x equals 70, and x equals 80, not including 80. We also see that the function is defined from 80 to 90 interval, not including 90. And we also realize that the function is defined from 90 to 100, including both 90 and 100. So we can mathematically say that this is closed interval and this is closed interval to the left but open interval to the right. And this is closed interval to the left and open interval to the right. Why did we pick to have an open interval to the right for 70 to 80 and 80 to 90? Because if we put this as closed interval, then we will annul the fact that this is a function. Why? Because we will have the vertical line test failure. So the function is not defined for C. When x is equal to 80, the function is not C. It's not defined for C, defined for B. And likewise at 90. And that's why the interval for B does not include 90. Otherwise, we will fall into the condition that annuls that this is a function. But over here, for the interval between 90 and 100, it includes its closed interval at the 90 edge, closed interval at the 100 edge, because there is no other score above 100. So, having stated so, we will go ahead and talk about the function. Now, this is like a step, so it's not really continuous. Why? Because it has what? It has jumps. This function has jumps, and a function to be continuous, it should not have any jumps. So the function is equal to a grade of C from 70, 71, 72, 73, all the way until 79, 79.5, 79.99, and then it jumps to B. It jumps to B at 80. So the function is not defined at 80 in this interval. It defined at 80 in the interval of the B, and so on. So this function is not continuous. Let's ask ourselves the second question. Is this function, or does this function have an inverse? And obviously from the diagram we can tell that it does not have inverse. Why? Because definition 2 states that a function has an inverse if and only if it is a one-to-one function and onto function. And if we look, it's not a one-to-one because 70 and 75 are mapped to C. It's also not onto because B is not mapped to. So this function is, it's not continuous, so the answer is no here. It doesn't have an inverse because it's not onto and it's not one-to-one. So the answers are no and no. Let's go ahead and answer this question. The graph function does not have an inverse. Why? We said for a function to have an inverse, it has to be one-to-one and onto. And this function is not onto. What does it mean to say a function has an inverse? That means if I move from the function 71 maps to C, then the inverse should take C back to 71. So the inverse, you can imagine it as imaginary, goes back to 71. Now, to demonstrate that this function does not have an inverse, we're going to move the range and put it where the domain is, and move the domain and put it where the range is, and rearrange the arrows. And that will give us the inverse. We cannot call it a function because we don't know if it is a function or not. So to do so, we will just go ahead and show. So this is the swapping. You can see the letter grade now in the domain area, and the percentages are on the range. We'll go back to the function just to ensure that we are in the same page. So to start with, this is the function. This is the percentages to the left, and this is the letter grade to the right. We will go to the inverse. This is the letter grade to the left and the percentages to the right, and we rearrange the arrows. If we look at this, it's not a function, obviously, because for it to be a function, every element in its domain must be mapped, and B is not mapped. Moreover, the element C is mapped to more than one element in the range. So this is another violation. So there are two violations here. So this is not a function, rather this is a relationship. So we could just name it a relationship. Score equal to a relationship on the grades, on the numerical grades. The score is equal to relationship on the grades. So score is 71, 92, or 75. It's relationship of the grade, the letter grade, A, B, or C. So if you know the letter grade, you plug it over here. Okay, it will tell you the score is 92. Letter grade is C, you plug it over here. It will tell you the score is either 92 or 75, and that's ambiguity, and that's why it's not a function. Let's go ahead and look at another function. This is a summary of the answer for the question. The function grade is not onto, thus its range is the domain for its inverse. As such, the inverse is not a function because it does not map the element B, which is right here. It's not mapped. It does not map the element B, and the element C leads to a jump because the element C connects to both 71 and 75, and there is a vertical line connecting 71 and 75 because C is the X value and these are the f of X value. So that's a violation there. Let's go ahead and continue to look at another function. This function relates the age of a child to the height, and the data for this is taken actually from the internet. We just took the data for the shortest infant or the shortest child. So symbolically, this is like 2 years. The average for the short is 20 inches. 3 years, the average for the short is 30, and 4 years, the average of the short is 40. Now the question is this function continuous? The function that relates the child age to the height, is it continuous? Height equal to f of the child age, function of the child age. Is it continuous? We cannot really tell from the diagram. Let's look at the graph of the function. Here is the plotting of the function. It's clear that at 2 it's 20, at 3 it's 30, at 4 it's 40. So this function is a linear function because it's a straight line. Since it's linear and since it's a straight line, we can look at, for example, 1.5. 1.5, it gives us a value of 15 for the height, and so on. 2.5, it will give us a value of 25. So between any two values, there are values, and the function is linear. So that means the function is continuous. Now, the next question, does the function has inverse? And we can see that the function is 1 to 1 and onto, so it has an inverse as well. So the answer is yes, yes. Let's take a look at another function. This is the function that relates the temperature to the season. Let's take a look at when the temperature reaches about 99 degrees Fahrenheit. This is definitely summer, unless there are exceptions. On the other hand, when the temperature is 10 degrees Fahrenheit, then this is usually the winter. And when the temperature is pleasant at 30 degrees Fahrenheit, then it's spring. Can we answer the questions without looking at the plot? This is a temperature and this is a season. Is this a continuous function? And is this a function that has inverse? Let's take a look at the plotting. Once again, the plotting also, this is taken from some of the data for the city of Chicago for one of the years. I don't know, 48 or 49, I don't remember. But anyway, we can see that the function is continuous. The function, although we just have samples, and like we said, we just put samples, but the temperature changes gradually. Temperature does not jump, changes gradually, and for that reason the function is continuous. And does the function have inverse? Based on the data that we have over here, because we have just these representatives and we're focusing on them, so it's one-to-one and onto. And if we're given that only 3 values in the domain and they told us 10, we're going to have to say it's winter. 99, we're going to have to say it is summer. 30, we will know that it is spring. And if we know that the answers are only these 3, if we are told summer, we cannot pick 10. We cannot pick 30. We have to take 99. So it's very, very clear that this is a one-to-one. So the answer is yes and yes too. So we'll go ahead and put yes, yes. Let's take a look at another function which relates the velocity to the distance. Likewise, we will just go ahead and jump and look at the function plotting. This is also real value, real world value plotting. So we will jump to answer the questions. Is the function continuous? We said the function is continuous if it does not have any jumps. This function doesn't have any jump. If you have an object that's moving, the move is not gonna skip some area and move, no vertical moves, so there are no jumps. The move will be horizontal, especially if the object is moving horizontally. So for that reason, the velocity and the distance relationship is indeed a function, and this function is continuous. Now, does it have inverse? Once again, based on the data that we're limiting over here, it's also a function that has inverse. So the answers are yes and yes. Let's take a look at another function. This function relates a country to its continent. And if we look closely, we have Saudi Arabia, and it says it's in Asia. United States, it says in North America. United Kingdom, it says it's in Europe. So this is a function that will give me the continent, the dependent variable, equal to the function of the country. Let's plot the function to answer the questions. We can see that the plotting is just points, discrete points. So this is not a function that is continuous. So this function is not continuous. So the answer to continuous is not. The answer to inverse, based on the data that we have, if anybody asks us, we have to choose between 3 countries, and then we said Asia. We cannot say the country is United States. We cannot say the country is United Kingdom. So it's got to be Saudi Arabia, because we have these 3. And if somebody told us that, okay, we're looking for US, United States, we have to pick between these 3. We cannot say it is in Asia. We cannot say it's in Europe. It has to be in North America. So we could go back and forth between them. So it is one-to-one and onto. But it's not continuous. Since it's one-to-one and onto, that means we have no here and we have yes over here. And that's it. We have no over here and we have yes on this side. We will continue, but now we're going to continue with different characteristics. We want to check if the same functions we evaluated, if the function is linear or not, and if the function is one-to-one or onto or neither. So let's just repeat the same functions, and before we could get to the functions, we will look at the definitions. A function is linear if its graph is a straight line. That is, if the maximum power of the independent variable is 1, then the function is linear. Definition number 2, a function is one-to-one if every element in its domain is mapped to an element in its range, and both the domain and the range have the same number of elements. The third definition, a function is onto if the mapping includes all the elements in its range. Now that we have these definitions, let's go ahead and check the same functions we went through. Let's go ahead and check them. First is the score and the grade. This is the function for the score and the grade. The question, is it linear? So before we could answer this question, we know that a function is linear if its graph is a straight line. So let's go ahead and take a look at the graph. Is the graph straight line? No, it's not straight line. It's like steps. So this is not a straight line, so the function is not linear. Is it one-to-one? The function is not one-to-one also, because B is not mapped to, and because we have 71 and 75 are mapped to a single value, so it's not one-to-one and it's not onto, and it's not linear, so it's neither. Now let's take a look at another function, which is the one that connects the child age with the height. So this is a function that, given the child age, it could give you the height of the child. And like we said, we looked at the shortest children. So 2 years, 20 inches, and so on. We spoke about them. Now we want to know if this is linear or not. And we know what linear is. Linear means the graph is a straight line. So let's take a look at the graph of this function. The graph is indeed straight line, so the function is linear. Now, is the function one-to-one and onto? Yes, it is one-to-one because every element in the domain is mapped to an element, a unique element in the range. And the number of elements is the same on the domain and range, so the function is onto. So our answer is that yes, the function is linear because it's straight line, and yes, the function is one-to-one onto because of the reason that we just explained. Let's take a look at next function. This is the function that have connection between the temperature and the season. Temperature equal to a function of the season, and we have the temperature to the left and obviously the season to the right. And before we could answer whether it's linear or not, let's plot the function and then take a look at it. A function is linear when it is straight line. So this is not straight line. The answer to linear is no. And this function is one-to-one onto. So the answer to this is yes. So it is not linear, but it is one-to-one and onto. Same conclusion we can also make by looking at the next function, which is about the distance. And the answers are the same. And the last function is about the country and the continent. And it's very obvious that it's not linear and it is indeed one-to-one onto. That's it. Thank you for watching the video, and please subscribe to the channel. You have a great day.